Hello everyone, my name is Sen Yang. I am a PhD student at Southeast University. This is a presentation for our ICCV paper, TransPose, Keypoint Localization via Transformer. This work was done with my collaboration at Southeast University, Zhibing Chen, Mu Nie, and Vanku Yang. In this paper, we aim to build a transformer-based human pose estimator that can capture and reveal the image-specific spatial dependencies. And especially, we want to use the self-attention layers in Transformer to capture and reveal the long-range interactions. Recent years, many successful deep scene-based models have emerged, such as TransPose, CPM, Stacked Hourglass Network, CPN, Simple Baseline, and Intranet. To localize the keypoint locations, the model usually needs to capture global relationships and local feature information. This induces many designs. Hourglass Network uses hourglass modules to obtain global information. CPM model repeats multiple stages to achieve a large receptive field. Intranet uses multi-scale fission and high-resolution representation. However, there are still some problems in the current models. 1. They need very deep layer to achieve a large receptive field. 2. The spatial relationships between body parts are implicitly encoded in the weights and activations of the neural network. 3. The spatial dependencies should be image-specific, but the weight of the convolution is static once the model has been trained. 4. There is lack of tools to visualize the dependencies of the predicted key points. Considering these problems, we think Transformer is exactly what we need for human pose estimation due to its strong ability of capturing long-range dependencies and its dynamic attention weights. Here we present the architecture. It is simple yet effective. The model includes 3 parts: a CNN to extract low-level features, a Transformer encoder to capture the relationships and interactions, and a head containing 1x1 convolution to predict the heat maps. We take the activation maximum position from the heat maps and the attention maps from the self-attention layers. We can acquire the dependency areas of the predicted key point locations by taking out the corresponding rows of the attention matrix. In this slide, we show that the attentions can be seen at the dependency areas of the activated locations. The heat map activation at location I can be approximated at the attention-weighted sum of the tokens from all image locations. Particularly, the last attention layer acts like an aggregator to collect the contributions from each location according to the attention weight. We evaluate our method on COCO dataset. The TransPose R model achieves competitive performances compared with simple baseline ResNet series, with significantly fewer model parameters and faster speed. Also, compared with Intranet baseline, our model achieves comparable performances with fewer model parameters and faster speeds. Motivated by the success of pre-training in LP and the recent VIT model, we transfer our COCO pre-trained models to MPII. The results show that fine-tuning the pre-trained models achieves significant improvement over only full training on MPII dataset. The improvements achieved by our pre-trained models are more obvious than the pre-trained Intranet. In the qualitative analysis, we choose the variables of scenes, keypoint types, images, and layers to study how these variables affect the behaviors of the model. ResNet S-based model prefers to attend to local image clues around the target joint. In contrast, Intranet-based model can exploit multiple longer-range clues to predict the key points. In summary, our qualitative analysis reviews the model behaviors under different conditions, which also give us insight into how the model handles special cases such as a collision. That's all. Thanks for your listening.